Have you ever wondered what the real difference is between a massive, sudden explosion and the slow, creeping rust that forms on a bicycle? I mean, they're both chemical reactions, but they happen at completely different speeds. Today, we're going to pull back the curtain and unlock the secrets to controlling that speed. And it all comes down to what's happening on a tiny, microscopic scale, right? Some reactions are just bam, over in a flash, while others can literally take years. So, what's the deal? How can we speed things up when we want to, or slow them down? That's the big question we're going to tackle. Okay, first things first, let's get our language right. When chemists talk about chemical speed, they're really talking about the rate of reaction. It's just a fancy way of measuring how fast our starting ingredients, the reactants, are getting used up, or how fast our final result, the product, is being made. Now, if you want to understand what controls this rate, there's really only one core idea you need to get your head around. It's the foundation for everything else we're going to talk about. Think of it as the collision rule. And here it is, the golden rule itself. To make a reaction go faster, you need two things. You need particles to collide more frequently, and you need those collisions to be more energetic. That's it. More frequent, more powerful collisions, that equals a faster reaction. Let's break that down. This whole idea comes from something called collision theory. And the first part is, well, it's pretty much common sense, right? For particles to react with each other, they have to physically bump into one another first. No collision, no reaction. It's as simple as that. But, and this is absolutely crucial, not just any old tap on the shoulder is going to work. A collision has to happen with enough energy, enough force, to actually break the old chemical bonds so new ones can form. That minimum energy requirement has a name. It's called the activation energy. Think of it like the minimum height to ride a roller coaster. If you're not tall enough, you're not getting on. So, to boil it all down, for a reaction to actually happen, two conditions have to be met. When a collision ticks both of those boxes, it happens, and it has enough energy, we call it a successful collision. The more of these successful collisions we can get, the faster our reaction will be. Great. So if our entire goal is to make more successful collisions happen, how do we actually do that? Well, in the world of chemistry, we have four main levers we can pull to make that happen. Let's take a look at each one. First step, temperature. When you heat particles, you're giving them a shot of kinetic energy, and they start zipping around like crazy. This does two amazing things for us. One, they obviously collide more often because they're moving faster. But two, and this is the big one, they collide with way more force. This means a much, much higher percentage of those collisions will have enough energy to overcome that activation energy barrier. Next, let's talk about concentration, or, if we're dealing with gases, pressure. This is all about crowding. Think about walking through an empty hallway versus a hallway packed with people. The more crowded it is, the more you're going to bump into someone. It's the same idea here. By increasing concentration, you're just squishing more particles into the same space. They're bound to collide more frequently, which in turn increases the number of successful collisions. Our third lever is surface area, and this one also works by boosting how often collisions happen. Imagine a solid sugar cube. Only the sugar particles on the very outside can react. But what if you smash that cube into a fine powder? You've just massively increased the surface area. Suddenly, way more particles are exposed and ready to react, which leads to a huge jump in the frequency of collisions and a much faster reaction. So far, we've talked about making particles collide more often or hit each other harder. But what if there was another way? What if you could somehow rig the game by changing the rules themselves? And this is exactly where our fourth and final lever comes into play: catalysts. These things are the ultimate chemical cheats. They basically provide a shortcut to get to the finish line faster. So what in the world is a catalyst? It's a substance that speeds up a reaction. But here is the truly magical part. It doesn't get used up in the process. It's like a helpful guide that shows you a shortcut, and once you're on your way, it just goes back to the start to help the next person. It's still there at the end, completely unchanged. So how do they work this magic? Well, catalysts don't make particles move faster or collide more often. Instead, they do something much smarter. Imagine you need to get over a huge mountain. That mountain is your activation energy. A catalyst doesn't give you a jetpack to fly over it. Instead, it shows you a secret tunnel that goes through the mountain. It provides an alternative pathway, and this new path has a much lower activation energy.
And this isn't just theory, it is absolutely essential for modern industry. Many of these catalysts are used to make things we rely on every single day. We use iron in the Haber process to make ammonia for fertilizers. We use vanadium oxide to make sulfuric acid. Catalysts are what make these huge industrial-scale processes efficient enough to even be possible.
Okay, we've covered a lot of theory, but how do scientists actually measure this stuff in a lab? How can you literally see the rate of a reaction? Well, let's look at two of the most common ways. One really simple way is to just watch for visual change. In this classic experiment, you mix two clear solutions and they react to form solid sulfur, which makes the whole mixture go cloudy. So all you do is draw a black cross on a piece of paper, put your flask on top, and time how long it takes for the cloudiness to completely hide the cross. Simple. Another popular method is to measure how much of a product you're making. So when you react something like marble chips with acid, it fizzes and produces carbon dioxide gas. You can collect that gas in a syringe and simply record how much volume you've collected every 30 seconds or so. This gives you a direct measurement of how the reaction is progressing. So, whether you're timing a disappearing cross or collecting gas in a syringe, you end up with a set of data. And when you plot that data on a graph, it tells a very clear and powerful story. And here is the single most important thing to remember about these graphs. The steeper the line, the faster the reaction. That slope, or gradient, is the rate of reaction. A really steep line at the beginning means the reaction is going full steam ahead. As the line starts to level off, it means the reaction is slowing down. And when that line goes completely flat, the reaction's done. It's stopped. So we've seen how temperature, concentration, surface area, and catalysts all control chemical speed in a lab. But this is also happening inside you, right this second. Your body uses biological catalysts called enzymes to control thousands of reactions. Which leaves us with a final thought to chew on. Based on everything we've just covered, what levers do you think your body is pulling to control those reactions at this very moment?